Good morning, Jim Chastain with EasyPower. Today's episode in the Refresher series is panel data options and how to improve productivity as you're working with panels. Very often the features are overlooked, but there are several built into EasyPower tool suites which can make life easier for those of us who design, build, and document projects with panels, whether there's a lot or a few. And so we're going to cover those today. A discussion of how the features can be utilized to extract certain information that may be important or useful in arcflash studies is also going to be touched on in custom schedules, because as you're working with certain clients or customers, they may have a requirement that doesn't fit the standard template for displays of schedules. So we're going to touch on that as well. There are four basic data entry methods to add component or circuit data to panels themselves. There's direct entry, which I would assume most users are exposed to or experienced with. There's panel library load, which requires customizing your ST standard library file, copy and paste, and then subsystem templates. We're going to go through examples with all four. Then we're going to show how to add outboard panels, both multi-phase and single phase, and how to set those up on a one line, and talk a little bit about the trade-offs involved. There may be multiple reasons for wanting to do this, not the least of which is being able to carry arcflash incident energy calculations down to the individual panel load, or if we want to coordinate against a large load that may be coming to a panel, both of which are easier if you add a subpanel or outboard daughter loads to an existing panel. So we're going to touch on that as well. At this point, we're going to be taking questions on the chat line. The audio is muted, so if we don't get to you during the presentation, by all means send us an email with your question and we'll have it followed up. So the first example is essentially a standalone panel that's set up under utility supply, and everything's at 480 volts. We're coming down to a standard 1 MVA transformer, and we have a single panel right now coming from this bus. Real briefly, we're going to look at the contents of this panel, and as you've been exposed to, you can enter data in the specifications tab, but most of it's for information only. Under incoming, we've detailed what cable comes down to this panel, what the main breaker, the fact that it has a main breaker, and what the device settings are. And then when we get to description, you'll see we have, on the left side at least, several different loads, and all the protective devices are spec'd out. The cable lengths were all set at 99 feet because I used auto design. When we get to the right side, we see that we have basically an empty panel and plenty of room for adding loads later on. A couple notes on the display that we're looking at. As you look at the basic panel schedule or the basic panel data file, there are a host of additional columns that can be utilized in various ways for various purposes, and you can reduce those, or the number that you're displaying. In this case, you go to configure, assign a name specifically to the display that you want, and then you just check the columns that you want to remain in the display for your purposes. You save it, and you're off and running. So now, as long as I'm in the Jim spreadsheet view, I always have the same column display when I open up a panel. Likewise, you'll notice here, very seldom do we talk about library schedules, but these are spreadsheets that have been set up in the library, in the device library. And in my case, I set up 4 custom schedules: one for 210-volt AC loads, one for hospitals, one for industrial projects and marinas, and then another one that I just play with. So for right now, we're going to leave it on industrial, and we're going to save it. And all that does is link that connection to this panel. Okay, so that pretty much resembles or overviews what could be done for direct data entry, where we select one of three loads: a standard linear load, a standard motor, or a subpanel. And as we select any of those, we start to enter the data in terms of how many phases it is and how many volt amps it draws on each particular phase. We'll get into more of that later. Now, as far as creating new panels, what I want to do is create three daughter panels to this one, and we're going to come at it from three different directions. First of all, I want to enter a outboarded motor. Second, I want to, from my subsystem tab, I come up to Insert, Subsystem. I have saved a copy of this existing panel as a template, and so now as I call it up, I can now put this into any one-line diagram I want, and it'll have the same contents as the one we start with. And then finally, I'm going to put a third panel, and we're going to start with just a blank slate to do it from scratch. Now, since each of these is outboarded from the other panel, the existing panel, we're going to take a cable and connect them in to each one. And the third. Now, I'm not going to worry about the cabling today, so I'm just going to copy and paste from an existing cable schedule. So I'm going to copy the value on this cable data, paste it in here, paste it in here, and paste it in here, assuming that all three cables are the same. And I'm going to go back to my options, and then from my cable data, I'm going to take it off of my one-line diagram. So while I have the name of the cable, I don't have necessarily the data for that cable displayed. So it cleans things up. Okay, first of all, we want to go in and characterize the motor. So we want the motor to be a significant load. 10 horsepower is fine. We click to calculate full load current. We click on calculate to get the X over R value, noting that the tool has decided it's less than 50 horsepower, and it's looking up the X over R from an ANSI lookup table, and we can plot the thermal limit curve if we so desire. So that's pretty much specified out everything that's required to add this as an outboard load to my panel. Okay, again, the existing one, we've got two ways to work. I can take a copy of what's here on the left side and just copy and paste. So as I left click and drag, I copy all of that, Control C, and now I go to the other panel. We're not going to worry about this for now. Open up this side, and under the description, let's put in 10, and we're going to Control V, and now we've dumped everything that was on the first panel into this panel on the left side. So we're going to save this. All right, let's go back and finish characterizing this one so it can be added to our. So we've got the cut and paste, or the copy and paste down. We look at the right side. There's still a lot of capabilities here. Let's go ahead and add a couple loads. First of all, let's add a three-phase motor. Let's make it 20 horsepower. As we do that, you can see the tool divides up the load, the VA load, or the amperage between phases. We're not going to worry about demand factor. I will go ahead and use auto design to size the protective device and the cable conductor. So you can see that we've got a square D part number. And let's go ahead and set up a three-phase linear loads. Let's say these are heaters in a remote building. So let's say we've got 2200 VA per phase in each of the three phases. And so as we finish with this, we're ready to do a summary. So we calculate everything that's downstream, tabulate it. So now we have a 100 amp panel, looks like a maximum 122, 23. So as we do that, it says the breaker's data is incomplete. So let's go back and check out the incoming breaker. We didn't tell it what cable we're connected to, so let's go verify that. We're on C3. And we need a 100 amp breaker. 225 ought to work. Short circuit looks good. Phase trip looks good. So we should be able to close it down. Okay, finally we're at the blank panel that we've just copied and pasted into. And here we want to use a fuse. We know it's coming from C4. We haven't really looked at the current that this is going to draw yet, but let's assume it's going to be somewhere up around 100 amps. Verifies the fuse is in the library, which it is. Go to the description, and just go ahead and do a quick summary on it. We can see right now we're at 67 amps, 82 amps. So we got a little bit of headroom. Let's go ahead and put a couple loads on the right side and just make them single phase. So these are all single phase breakers, and we might as well size those while we're at it. And the third one. All right, so we're ready to tabulate this summary. And we're up to 75. Thinks that sounds pretty good. Let's go ahead and close it. Breaker's all fine. So now we just need to bring these in to the mother panel. And since they are all outboarded, we're going to again, the left-hand side is full, so the right-hand side is where we want to add these. They're all three-phase panels, and they're going to be considered subpanels. So the first one's on C2. Because it's a motor, it's not going to show up as a panel. And because we don't have the details from that particular load, you can see everything is grayed out because we'll have to bring that in with the summary as it summarizes downstream loads. Likewise on the first panel, I didn't tell it's three-phase, so this one's three-phase. The next one's going to be a three-phase sub-panel, except there's actually a panel here on C3, and it looks like it's panel 1A. Three phases. Same difference. We can't determine what the load is until we do a summary. So let's put the other panel on C4, and then make it three phases. Okay, so the one thing we haven't done, we've copied and pasted, we've entered directly, we're piping in subpanels. The one thing we haven't shown is our library schedule, and as we talked before, we had a library that we use for the industrial plants, and so as we've linked this up, we have the ability now to go out on that schedule and pull in preset loads. So let's set, we want 100 amp A phase load, circuit set up, 100 amp B phase, and 100 amp C phase. Now the advantage here is I've already got these sized, and the cables that we traditionally use are set up here for 55 feet. And it seems like I had a, let's go all the way back to the library load. Seems like I had a 3-phase 5 horsepower motor. So let's use that. So now, as we've entered each of these loads from this, we'll go to the library and see how these are set up shortly. But now, as we're finished, we can summarize the downstream loads and pull these in. So now we've got a 430 some amp panel. Obviously, we set this up for 225, so it's telling us we need to deal with this because we've got too much load on here based upon the breaker size that we'd set up. So let's go in and verify this. We got a main breaker, 225 amp. Let's jump up a little bit here and deal with a 400 amp panel. Calculate short circuit. We're not going to change anything on the phase trip. See if it'll handle that. Okay, so at this point we've added loads, we've adjusted breakers, and we're ready to calculate arc flash incident energy and make sure that everything's under control. Let's see if we've missed anything. Okay, so we've got our arc flash incident energy taken out of the bus level. So now the two things we wanted to do in addition to this was go back to our database editor and outboard a couple lighting panels. So we're starting out with 480 volts. We know that we need a step-down transformer to 240. So we're going to take this and wire it into a sub-panel socket here, and then set up a couple loads, downstream panels. And these will handle just the same, except now these will be at 210. Now, as we do this, what did I pick up there? We're accurately describing what the phase distribution is for these going out to subpanels. But what you'll see is we have a 210 line-to-line voltage available, and going from line to ground, we get 120 volts out of it. It's not quite the same as a split phase system that we see in residential applications, but certainly we see this fairly frequently in industrial applications. All right, so in many of these, let's say we have just a fuse, and this is from C7, and let's say we want to set this up as a 50 amp or 60 amp panel. Let's see what we got. Verify short circuit, and we don't have a switch involved. Okay, so let's go up and set up 5 rows. Now the same kind of thing is I may set up a library load for 210 volt systems. So I'm going to link that and then reopen it. And as I go in and bring in the loads here, we could have a 15 amp A, 15 amp B, and a 15 amp C. Although I think this would only be a 2-phase coming off of 2-phase to ground. So let's take this one out. Each of these are 2-phase, single-phase loads, but they're going across a 210 volt supply. All righty, gotta get rid of this one. In fact, I'm just going to erase the whole row. All right, so this brings my summary for this panel up. Looks like it's only 10 amps, 20 amps, or 0.2 of an amp, hardly anything. Let's go back and look. 15 VA is only a 1/10 of an amp. All right, so that's a lighting panel. So let's bring it back into this one. Exactly the same deal. I'm going to go ahead and set up with a fuse. It's going to be on C6, which is upstream. We're going to make this a fuse, Aeroflex, and let's go and make it a 100 amp load or a 60 amp load or a 50 amp load. And then let's, besides putting our outboarded panel here, we'll also bring in, so this will be on a single circuit. It is on C7 and it is this panel. And now let's bring in some heavier loads. So let's say single phase 2200 VA, single phase 2200 VA, 2200. Summarize this, calculate it. All right, now we got this thing up to 20 some odd amps, and we're good to go. All right, so what are we missing? Cables. Let's take a copy of this cable and paste it here. I guess we also need to update our transformer. And clearly you wouldn't need as heavy a cabling as we used up on the 480 volt bus, but for purposes of speeding up the process, we're using the same size cable that we used on the 480. Alrighty, this will be a 75 kVA. We're going to calculate it. Impedance is 3%. Calculate that. Save it. See if we got enough to go in a short circuit. Calculate our arc flash. So the only thing's out of control. So this is a good question. We've got, so I mentioned earlier that these are not split phase circuits. These are single phase, and EasyPower, when calculating arc flash, deals with only balanced three-phase systems. So there is going to be some error built into these single phase calculations, and a case in point is, especially at lower voltage, we could have artificially high incident energy calculations because of IEEE model being a little bit skewed towards the medium voltages between 400 and 1,000 and less accurate in less than 240 volt range. This is a function of our arc flash controls, which allows us to change the maximum arcing time if we need to do so on any voltage spectrum. Well, before I start doing that, the first thing I want to look at is my arc flash spreadsheet. So I'm looking at bus 5, and I'm trying to figure out why it's so high in energy, and I see PL1 main is the limiting factor for current, and currently it's got an arc flash of 2,407 volts. Well, let's kind of look at this. I've got, okay, it's on a 240 side, so it's 210 volts. Panel 1 main is up here at 480, and we haven't specified the size of the breaker going down to this transformer. So I guess that's where the first place we want to start, because on the high side we're protecting incident energy here on the 480 volts, but we haven't done anything on the low side. So let's kind of go back and look at that. Again, we could do the same result for limiting the maximum time. If we look at bus 5, we see that the arc flash trip time is 40 seconds. Well, that's unrealistic in anybody's book. So certainly we could limit it with a maximum time, but because we don't have a protective device suitably sized, I think it's premature to go in and change the time. So let's go back into our database editor, save the changes we've done so far. Let's look at the breaker now on C5, subpanel C5, and figure out why it didn't get sized to the right. Did we even add it in? All right, so it's not under these. Okay, here's a motor, here's a load, and we don't have C5. All right, so let's fix that. So we got to set up subpanel C5, and this is going to, where is this going? C5 is going down to, need to expand that out before I make a decision. So panel 3. So it gave me a choice of panel 3 or panel 4. Let's go to panel 3. So again, subpanel 3. And we don't have a molded case circuit breaker set up yet. So let's go ahead and take the summary, bring the summary up. And let's go back in and set up the breaker on that circuit. And the place it wants us to set it up is under this data dialog box. All right, so let's use square D molded case circuit breaker. My handy dandy E-frame, EGB. Should give us 125 amp. We need something much smaller than that, so let's set it up for 40 amps. Shouldn't change the summary, but let's go ahead and do it anyway. And save it. Now let's see what our short circuit energy is. Okay, now the transformer is under control. Okay, if we look at the arcflash spreadsheet, now we're looking at bus 5. Now the device that's tripping is still panel 1A. And its maximum trip time is, let's verify that we update everything. Its maximum trip time is now 148 milliseconds. So there really is no time, there's no reason to limit the trip time on this breaker artificially. Okay, so what have we done so far? We've added, we've populated breakers, panels with copy and paste, with subsystems, with raw data or bare entry. We've entered subpanels. We've conducted arcflash studies on single phase, albeit a little bit conservative. It's still within the parameters of safety, and I think we've done a pretty good job of covering the subject. So that's going to conclude today's schedule. And so the last thing I guess I wanted to do was show my schedule, highlight the panel, right-click, insert schedule. And then if we want to, we can customize this by going out and picking up a custom panel schedule that's got arcflash data, room for arcflash data. So now as we put this into the one line, you can see we got interrupt current, and these blanks are empty. What we're going to do is go back, fault, and store the symmetrical current. You can see that we've got that now on our schedule, and then fault and store arcflash energy, and now we've got our arcflash boundary in inches, our PPE, and our incident energy. So again, success. We've saved the world, and we're ready to close out the session. Any questions? Feel free to shoot me an email, jim@easypower.com, and we hope to talk to you the next time we have a refresher training. Have a good day.